Okay, so I think we should just start now. So, hello everyone, and welcome again for the live sessions for the NPTEL course Introduction to Semiconductor Devices. This is live session number 11 for the week 11 of this course, being instructed by the Professor N.K. Emani of IIT Hyderabad, and I'm Samadhan, your PMRF TA for conducting these sessions. So the plan for the sessions from my side is quite simple, as you know till now that in the first quarter of this session I'll briefly cover the recap of the session, recap of the week's content, this week's content. That will give you quite a nice refresher going forward in solving the assignment problems. Then we'll move to the problem solving part, in which I'll cover the problems based on previous year's assignments, which are quite similar to your current set of assignments, and also the questions appeared in competitive exams such as GATE related to this week's content. So without further ado, let us get started with this week's lecture content overview. So in the last 10 weeks of the course, we have basically looked at the electronic devices. We have understood how to analyze these particular devices, their properties in quite a sufficient depth. So now in the last 2 weeks of this course, beginning from this Monday, we would like to focus on the class of devices called as the optoelectronic devices. And why are we interested in them? Well, it turns out that the optoelectronic devices, or the so-called photonic devices, are quite important and crucial part of the current technology. So for example, we see solar cells, LEDs, which are light emitting diodes, lasers, all of these. Just a moment. Okay, so as I was mentioning, moment please. Okay, so as I was mentioning, we see solar cells, light emitting diodes, lasers. These are all fall in the category of optoelectronic devices, and we can apply the concepts that we have learned so far in the past 10 weeks or so to understand how these devices actually work and function. So because of this crucial and critical importance of this technology, we would like to discuss these class of devices now. So the semiconductor devices can be designed to convert optical energy into electrical energy, and vice versa, that is to convert electrical signals into the optical signals. And these devices are used in like broadband communications, data transmissions over optical fibers, and so on. So the general classification of these devices is called optoelectronics, as I was mentioning earlier also. So in this week particularly, what we do is we discuss the basic principles of photo like optical devices, their principles, especially of solar cells, several photo detectors we have discussed the professor in the regular lectures. So solar cells and photo detectors convert optical energy into the electrical energy, and the light emitting diodes or the lasers or the laser diodes convert the electrical signal into the optical signals. So let us start with let me go to my slide number. Yeah, so let us start with the optical absorption. That is quite an important principle to begin with while studying these optoelectronic devices. So just a moment. Yeah, so when a semiconductor is illuminated with light, the photons may be absorbed, or they may propagate through the semiconductor, depending on the photon energy and on the band gap energy, that is EG. If the photon energy is less than the band gap energy, the photons are not readily absorbed, and in this case the light is transmitted through the material, and the semiconductor material or any material appears to be transparent.
The screen is not visible
Um,
properly.
Screen, I mean, my presentation, can you see my presentation?
Yes, no sir, clear नहीं है छोटा सा है.
Okay, so what you can do is you can like pin my screen or make it full screen? That would be better. Is it possible for you to do that? Just long press on my screen, you can pin it or make it full screen. That will.
Yes, sir. Yes, sir.
Okay, good. So as I was mentioning, if the photon energy is less than the band gap energy, the photons are not readily absorbed, and in this case the light is transmitted through the material, and the material is appeared to be transparent. If energy, that is h nu or h cross omega, is more than the band gap energy, the photon can interact with the valence electron and elevate the electrons into the conduction band from the valence band. And the valence band contains many electrons, and we know the conduction band contains many empty states. So the probability of this interaction is high when the h nu, that is the incident energy, is larger than the band gap energy. So this interaction creates an electron in the conduction band and a hole in the valence band, so that we can get an electron hole pair. Okay, so the basic absorption process for different values of h nu are shown in this particular figure 14.1. So when a light of energy h nu, let's say, is incident on a material of band gap Eg, in this case h nu is more than Eg, then the photon absorption takes place and the intensity of the photon flux decreases exponentially with the absorption coefficient alpha and also the distance or the thickness of the material slab. So this is the relation. So uh, when a photon of energy, sufficient energy, is incident on a slab, its intensity falls exponentially with these two parameters of interest. One is just a moment. Yeah, one is alpha, which is the absorption coefficient, and d is the thickness of the slab. So here you can see that for different values of alpha, I have the plot of the intensity versus x, that the distance is given. So we can expect from the equation itself that if you have larger alpha, that is larger absorption coefficient, the intensity falls quite rapidly, that is it gets absorbed in lesser distance as compared to the smaller alpha sample. Okay, then we move on to different class of materials called as the solar cells. So let us consider a PN junction as shown in this particular figure with a resistive load. A resistor as a load in the external circuit is being placed. Even with the zero applied bias to the junction, an electric field exists in the space charge region as shown in the figure. So when incident photon illumination can create electron hole pairs in the space charge region, that will be swept out, producing the photocurrent, let us denote it by IL, in the reverse bias direction as shown here. So the photocurrent, that is IL, produces a voltage drop across the resistive load, that is our external circuit, which forward biases the PN junction. And the forward bias voltage produces a forward bias current IF as indicated in the figure, and the net PN junction current then in the reverse bias direction is given by IL minus IF. So the the load current minus the forward biased current, IL minus IF. IF we know is given by this particular form. So the net current is given like this. So there are two limiting cases of interest, two like extreme cases. So the first is the short circuit condition. First is the short circuit condition, in which when our resistor is zero, moment. Yeah. So as I was telling, the short circuit condition in which our external resistor R is zero, and so that our voltage will also be zero, and in this case the current is referred to as the short circuit current, and it is given by I, which is equal to the short circuit current, which is equal to the only the load current and not the forward bias current. The second case Yeah. So the second case, second limiting case indeed, is the open circuit condition. Open circuit condition in which the resistor is effectively the infinite value, and the net current in this case is obviously zero, and the voltage produced in this case is called as the open circuit voltage, and the photocurrent is just balanced by the forward bias junction current, uh, and we have the photocurrent given by this particular relation over here. Okay, also the load voltage, that is Vm, that corresponds to the maximum power delivered, that is maximum power will be delivered when the dp by dv is essentially 0, and that is given by this particular relation. I am just summarizing here few relations here. Also, one important quantity is the conversion efficiency of a solar cell. So the conversion efficiency and it is nothing but the ratio of the output electrical power to the incidental optical power. So eta is output electrical power to the incidental optical power. So this is the efficiency, and the maximum possible current and the maximum possible voltage in the solar cell are given by ISC and VOC. ISC is the short circuit current and VOC is the open circuit voltage, and the ratio, and this ratio of VMIM by ISC VOC is called as the fill factor and is a measure of the realizable power from the solar cell. Typically the fill factor is between around 0.7 to 0.8. So this is the maximum realizable power from the solar cell. It is not 1, that would be ideal, but generally in between of 0.7 and 0.8. Okay, so let us go to our final slide for the summary, and then we moved to the class of optical devices called as the photo detectors. So there are several semiconductor devices that can be used to detect the presence of photons, and these devices are called as the photo detectors. So in a phrase I can say that these are used to detect the presence of photons, detect photons. Okay, so these devices are photo detectors. What they do is they convert optical signals into the electrical signals, obviously, and when excess electrons and holes are generated in a semiconductor, there is an increase in the conductivity of the material, and this change in conductivity is actually the basis of the photoconductor principle and perhaps the simplest type of photodetector. So let's say if electrons and holes are generated within the space charge region of a PN junction, then they will be separated by the electric field and a current will be produced. So the PN junction is the basis of several photodetector devices, including the photodiode and the phototransistors. So let us consider first the photoconductor. Okay, so this figure shows a bar of a semiconductor material with ohmic contacts at each end, and a voltage is applied between the terminals. The initial thermal equilibrium conductivity is given by this particular relationship, and if excess carriers are generated in the semiconductor, the conductivity then becomes equation number 2 in this particular slide, where dn, that is delta n, and delta p are the excess electron and hole concentrations respectively. The change in the conductivity due to the optical excitation, which is nothing but the photoconductivity, is given by delta sigma, and in terms of delta n and delta p, and the mobilities etc. is given by this particular equation. An electric field E, capital E, is induced by the applied voltage, and which produces a current caused by the drift of carriers. We saw the drift current with a velocity say Vd, which is nothing but the mobility times the electric field, and the electron transit time given by Tn, which is length over the mobility times the electric field. The photocurrent then is given by this particular relationship. So JL is the photocurrent density, area is its like the cross-sectional area, and in terms of these different parameters, the photocurrent is given by this particular equation. Okay, also we may define another important parameter, that is a photoconductor gain. So photoconductor gain lambda ph. Okay, so it is nothing but the ratio of the rate at which charge is collected by the contacts to the rate at which charge is generated within the photoconductor. Okay, so we can write this particular parameter as the current over this particular factor, and using the equation for IL, we can simplify it, and we get it in terms of the mobility and the time constants, and the Tn is the thickness. So the photoconductor gain is given by this particular relationship. Okay, also one of the other class of photodetector we saw is the PIN photodiode. So PIN photodiode, it is given, it is shown by this particular figure here. So the motivation is as follows. So in many photodetector applications, the speed of response is a key and a very important property. Therefore, the prompt photocurrent generated in the space charge region is the only photocurrent of the interest. So to increase the photodetector sensitivity, the depletion region width should be made as large as possible, and this can be achieved in a PIN diode, PIN photodiode. So as you can see, the PIN diode consists of a P region and a N region separated by an intrinsic region. This is an intrinsic region. A sketch of these is shown here, and the intrinsic region width, which is W in this case, is much larger than the space charge width of a normal PN junction. And if a reverse bias is applied to the PIN diode, the space charge region extends completely throughout the intrinsic region, and we get a very nice sensitivity. Okay, so I think this forms like this ends my summary of this week's content, and we should now begin with the assignment problems. So let us start with the problem number 1. So it is a simple problem based on a formula. So the problem is as follows. Consider a slab of silicon which is of 5 micron thick. Determine the percentage of photon energy that will pass through the slab if the photon of wavelength 0.8 micron is incident on it. Assume the absorption coefficient alpha to be 10 to the power 3 per centimeter. Okay, so different parameters are given, and we need to determine the percent of photon energy, determine percent of photon energy that will pass through the slab. So transmitted energy or transmitted fraction is what we need to determine. So if you go to our slide number 1 for optical absorption, we saw that the fraction is given by this particular relation in which it exponentially decays. So we can use it readily here. So the fraction is an exponential function of the absorption coefficient and the thickness. This is what we have to determine. So I over I naught. Let us just substitute it. Exponential of alpha is 10 to the power 3. It is in centimeter times d, which is 5 micron. For the consistency of unit, we need to make it in centimeter, that is 5 micron, that is 10 to the power minus 4 centimeter. So the exponential quantity as we want is unit less. So if you just calculate this, which will be like exponential of -4 -3 -1, that is -0.5. So it will come out to be around 0.6. So the transmitted intensity or transmitted energy, which are directly proportional to each other, is 0.6 times the transmitted is 0.6 times the incident one, which is nothing but 60% of the incident I transmitted. So our answer is 60% of 60% of the photon energy that will pass through the slab, that will pass. Okay, so 60% will be passed. Okay, so let us go to question number 2 then, if it is clear. If you can stop me if you have any doubt. Okay, so going to the question number 2. Okay, in this case, 1 centimeter by 1 centimeter silicon solar cell has a saturation current of 1 picoampere and is illuminated with sunlight, yielding a short circuit photocurrent of 25 milliampere. Okay, so the short circuit photocurrent is given. The maximum output power is 12 milliwatt. So the maximum output power is also given. Assume power of sun to be 100 milliwatt per centimeter square. What is the approximate fill factor? And a hint is given that we need to calculate the open circuit voltage. Okay, so fill factor is the one that we need to determine. Okay, so if we go to our summary slide, we'll get the formula for fill factor, and which is nothing but VMIM by VOC times ISC. Again, a simple formula, we'll write our fill factor, which is VMIM over VOC, that is open circuit voltage, times ISC, that is short circuit current. So the short circuit photocurrent is given excuse me, which is 25 milliamp. So ISC is known. Then the maximum output power is given as 12 milliwatt. So we know that power is nothing but V times I, and output power is given, that is PM. That means Vm times Im is also given, which is 12 milliwatt. So these two parameters are also known, and what we need to find out is the VOC. So for VOC, let us go to our formula section and see if we can find one. Okay, so this formula will give us the VOC, that is Vt times ln of 1 plus IL over IS. Okay, so let us do that. Okay, so VOC given by Kt over Q, that is Vt times ln of 1 plus IL over IS is saturation. Okay, I can write. One more thing we showed in one of the limiting cases is that when in the short circuit case, the IL is nothing but IS. So for IL, we can readily substitute our ISC, that is short circuit current. So let me first of all find out VOC. If we just substitute different parameters, so let us do it in the SI units first. So K is 1.38 times 10 to the power minus 23 times temperature. We can take room temperature 300 Kelvin divided by the electronic charge as 1.6 times 10 to the power minus 19 times ln of 1 plus IL, as I said in the short circuit case, can be substituted by ISC, and ISC is given by 25 milliamp. 25 times 10 to the power minus 3 amp divided by I saturation. The saturation current is given as 1 picoamp. 1 picoamp is nothing but 10 to the power minus 12 amp. Okay, So if we just compute it, we'll get some VOC that we need to substitute in the fill factor. So the fill factor is nothing but Pm times Im, that is Pm given by 12 milliwatt. So 12 times 10 to the power minus 3 watt divided by VOC, which will be this particular thing computed, VOC times ISC. ISC is nothing but what it is, 25 milliamp, that is 25 times 10 to the power minus 3 amps. Amp times volt would be again power will cancel. So fill factor, which is a unitless quantity, in our case would correspond to about approximately 0.8. You just compute it and you will get it around 0.8. So the approximate fill factor is 0.8. Okay. Is it clear? If you have any doubt, you can stop me, as I said. Okay, so after these calculations, let us go to some conceptual question. So this is the common data for question number 3 and question number 4. So consider the following devices, 5 of them, in order as solar cells, charge coupled device, that is CCD, LEDs, which is nothing but the light emitting diode, and lasers and photo detectors. So consider these following devices and answer question number 3 and 4. I think I want answers from you guys. So the question number 3 is as follows. The devices which can convert light energy, or say light, into the electricity are. So light to electricity is asked first. Question 3 is light to electricity. Okay, so uh, can you just unmute yourself and try to answer this question?
Solar cell.
Solar cell. Solar cell is what? It converts light into electricity. Okay, one is done. So CCD is also one of the photo detectors in which a fallen light creates charges, and it is a little sophisticated, but it is also again uh, a photo detector of a thing. So it also converts light into electricity. So 2 is also a light to electricity converter. What about LEDs? What do you think LEDs do?
Electricity to light.
Exactly. So this is not the light to electricity. Then going to for lasers. Lasers again is also electricity is given as input, and it gives us photons, that is light. So fourth, fifth, third and fourth is not the answer. And photo detectors, indeed we saw, converts light into electricity. So 1, 2 and 5 is our answer for question number 3. So the devices which can convert light energy into electricity are 1, 2 and 5, which is nothing but solar cells, charge coupled devices and photo detectors. Okay, so that means question number 4 would be exactly opposite of that, and which is the devices which can convert electricity into light. So as we discussed already, electricity, so LEDs which convert input electricity into output photons, that is light, and solar cells are also the same thing. So 3 and 4 are our answers for 3 and 4. Okay, so any doubt in this? I can see some chat. Okay, somebody is saying screen is not clear. Padmavati, can you just pin my screen? Probably that would be the reason. Pin my screen or make it full screen, then only you would be able to see it properly.
Okay, sir.
Okay. Okay, so then we'll move to the question number 5th then, if you don't have any doubt. Okay, so the question number 5th is again a formula based question. I'll just read out the objective for you. Okay, so the question goes as follows. Calculate the photoconductor gain of a silicon photoconductor. Okay, so the question is, consider an N-type silicon photodetector with length of around 100 micron. Length is given. The cross-sectional area is given of 10 to the power minus 7 centimeters squared, and the minority carrier lifetime is given as 10 to the power minus 6 seconds, that is 1 microsecond. Let the applied voltage be 10 volts. So based on these parameters, we need to find out the photoconductor gain of a silicon photoconductor. Okay, so based on the formula, if you go to slide number 3 for the summary, here the photoconductor gain is given by this particular relation. If you know these parameters, we can find it out easily. So let us do that. Just a moment. Here. So first of all, we need to find out the electron transit time. So electron transit time, which is one of the parameters in the formula, and it is given by electron transit time, that is Tn, as L over the mobility times the electric field. And if you substitute for electric field, which is nothing but voltage per unit length, so we'll have L times L times mobility times voltage. Voltage per unit length is the electric field, so L square times mu phi. So we know the L, that is 100 micron, that is 100 times 10 to the power minus 4 centimeter. It's squared divided by the mobility times the voltage. Mobility not given here, but this is one of the input, which is 1350, sorry, times the voltage, which is 10. If you just calculate it, you will get the electron transit time as 7.41 times 10 to the power minus 9 seconds. Okay, so let us just substitute in our photoconductor gain, which is given by photoconductor, that is lambda photoconductor is tau p by Tn in terms of 1 plus mu p by mu n. Mu p and mu n also are inputs. So if we just substitute tau p, which is 10 to the power minus 6 seconds, divided by 10 to the power 1.41 times 10 to the power minus 9 second, the transit time that we calculated, and the mobilities, if we substitute, you will get the photoconductor gain as 1.83 times 10 to the power 2. Again, this is a unitless quantity, which is a constant parameter. One more interesting comment that we can make here is that the fact that a photoconductor, which is simply a bar of a semiconductor material, has a gain. This may be a surprising fact, but I think you guys should ponder upon it, that a bare semiconductor material, a slab of a material, has gain. So that is quite an interesting point to just ponder upon. Okay, so let us move to question number 6 then. Here. Okay, so this question, consider a consider a 1 centimeter squared long silicon PN junction with a reverse bias voltage of 1 volt at the room temperature around 300 Kelvin. The diode has the following parameters, like the doping concentrations and other parameters are given here. Optical absorption coefficient is also given. Now a photon of energy of about 1.7 electron volt is incident on it with a power density of 10 watt per centimeter squared, and calculate the approximate photocurrent in the diode in ampere. Okay, so first of all, we'll assume that the carrier generation rate is constant, which is a fairly good approximation for the silicon, in which the alpha is quite small. So first of all, we'll need to find out the values of different parameters like GL, the width, the LP and Ln to find out the photocurrent. So which is given by this formula. If you go, this is the formula. So we want to find out it, but we need some parameters to be determined first. So let us determine those first. The first is the GL, which is the carrier generation rate. Yeah, GL, which is the carrier generation rate, and GL is given by the alpha, which is the optical absorption coefficient, times the output power over the energy, that is h cross omega. So in our case, if we just substitute it, alpha is 10 to the power 3 times the output power is 10 watt per centimeter squared times the energy. So h cross omega, if I put, is around 1.7 times 1.6 times 10 to the power minus 19 joule, and we'll get the value of GL then as 3.68 times 10 to the power 22 centimeter cube per centimeter cube per second. One parameter is done. Let us find out the built-in potential, VBI. We have seen it in quite detail, the built-in potential, which is nothing but the kBT times ln of Nn over Np. If we just substitute it, it will give us VBI of 0.85 electron volt. Now we know these two parameters. Let us find out the depletion width, that is W. So for that, we know the formula. We have seen it in the I think 6th or 7th week. 2 times the epsilon times the built-in potential plus the reverse bias voltage divided by the electronic charge times the Na plus Nd over Na times Nd. Na and Nd are the doping concentrations. Again, a mere substitution will get the depletion width as 1.8 times 10 to the power minus 5 centimeter, around 18 micron, I guess. Sorry, 0.18 micron. Okay, so diffusion lengths are also needed to be found out. So diffusion length also, we know the formula, we have seen it already. In terms of dp and tp is dp tau p and ln in terms of d and tau n. Again, mere substitution, I am just writing the final answer here. It comes out to be 8.9 times 10 to the power minus 4 centimeter, the diffusion length for the holes. For diffusion length for the negative charge carriers is 10.95 times 10 to the power minus 4 centimeter. Okay, so that was quite some calculations. So we have got all the parameters required based on the given inputs to determine the photocurrent. So the photocurrent is given by IL, nothing but the electronic charge times the carrier generation rate times the LP plus Ln plus W, which is depletion width, times the area of the material. So if you just substitute again, 1.6 times 10 to the power minus 19 times the GL that we got, 3.6 times 10 to the power 22 times the LP plus Ln, which is 8.94 times 10 to the power minus 4 plus 10.9 times 10 to the power minus 4 plus the width, that is 1.8 times 10 to the power minus 5 times the area, which is 1 centimeter squared. It is 1 centimeter squared. Okay, if you just compute it, we'll get the photocurrent as IL the photocurrent IL as 11.8 or approximately 12 ampere. It is one of the options, 12 amperes. We can click the option. Okay, so let us go to, I think it is misprinted. It is the final question indeed. Okay, so the question is as follows: a photodiode has a responsivity of 0.5 ampere per watt at 850 nanometer. Find the percent efficiency of the detector. Okay, so we know we have seen that the one of the figures of merit or the performance parameter is the responsivity of a detector, which is the ratio of the generated photo current, that is IPH, ratio of the generated photo current to the optical power, which is input incident on the detector. So the responsivity R lambda is simply the photocurrent generated over the optical power, that is P in. Also, the quantum efficiency is another parameter, which is quantum efficiency eta, we can say, is the number of electrons generated per number of incident photons, and it is given by P in over the incident energy h nu. So if you just compare these two, and if you substitute for Pn and for, if you compare these two, we'll get the responsivity, which is IPH by Pn. P in will get it as Q eta over h nu. If we just rearrange it, eta over hc by q lambda, and if you just calculate hc by q, it comes around 1.24. Eta times lambda, if lambda goes into numerator, eta times lambda over 1.24. Remember lambda in micron. So we have R lambda, which is a responsivity of a detector, then eta, which is the quantum efficiency, lambda, which is the wavelength of the incident photon. So these three are parameters related to each other. So we need to find out the percent efficiency, that is eta. So from this particular relation we can get eta simply as R lambda times 1.24 divided by lambda. R lambda is given by 0.5 ampere per watt, 0.5 ampere per watt times 1.24 divided by lambda, which is 850 nanometer in terms of micron. So make sure it is in the microns, and you will get the value of percent efficiency. Okay, so it comes around 73. So it is around 73%. Okay, so now let us move to our final, I think one more bonus question I have, and this is I have taken from the previous GATE paper, that is for EC GATE 2020, and the question is interesting question. The question is as follows: a PN junction solar cell of area 1 centimeter squared is given. It is illuminated uniformly with 100 milliwatt per centimeter squared of power and has the following parameters such as efficiency of 15%, open circuit voltage of 0.7 volt, fill factor of 0.8, thickness of 200 micron. The charge of the electron is given by 1.6 times 10 to the power minus 19 coulomb, as you know, and the average optical generation rate is asked in per centimeter cube per second. Okay, so let us start. We know that the fill factor, we know that in the solar cell the fill factor FF is given by Vm Im over ISC VOC that we saw earlier, and also the eta, the efficiency is given by Vm Im over P in percent, it is times 100. So if you just substitute, compare these, so if you substitute in terms of fill factor, eta would be fill factor times VOCISC divided by P in. So Vm Im I am substituting for fill factor times ISC VOC here, times 100 obviously. Okay, so we know that eta given as 15%. So 15 is nothing but fill factor is 0.8 times VOC is 0.7 open circuit voltage times the ISC, the short circuit current, times 100 divided by P in is 100 milliwatt per centimeter squared. So we get the ISC value, and if you just calculate it, you will get ISC value from this particular relation. Now also we know that the optical generation rate can be calculated by this particular relation, in which the short circuit current density, which is nothing but the short circuit current per unit area in terms of where T is the thickness and GL is the average optical generation rate, so which is simply EGL times the thickness. So ISC in this case would be then EGL times thickness times area. Okay, and therefore GL, which is our quantity of interest, would be ISC divided by E times T. And if you substitute ISC from here, 15 divided by 56, and so this is just mere substitution, you can do it. 1.6 times 10 to the power minus 19, P is 200 times 10 to the power minus 4, so we'll get the value of GL, which is the average optical generation rate in terms of in per centimeter cube per second, as 0.84 times 10 to the power 19. Push. Okay, so we get our parameter that we wanted to calculate. Okay, so this brings me to my final slide. Thank you everyone again for joining for this particular session, and I hope you like learned something. I hope to see you all in the next live session scheduled on the 14th of October, Friday at 6 p.m. And indeed that would be the last live session for this particular course, the 12th live session. I hope to see you all there. And as I always said, meanwhile you can go to my YouTube channel to see the recordings of these live sessions, and you can always go and refer them. Okay, so that's it from my side for this week's live session, and I hope to see you in the next live session. Till then, have a nice time. Bye bye.